Hi guys, welcome to your first Distance Friday. I want to encourage you all to treat this as much like normal class as possible. So even if you're sitting there in your pajamas, eating a bowl of cereal at the kitchen table, go ahead and get out a piece of paper. We're going to take notes. It's just like a normal lesson. The technology has been a little finicky with me, so just be a little patient as I get ready here. I've only been able to have my document camera can't go back and forth for some reason, so I'm gonna have to get my document camera ready and on our notes. Go ahead and get out a piece of paper. We are going to be talking, we are going to be talking about inverse functions today. So still functions, but a specific type of function. That looks pretty good. So first, just a recap. Remember that to be a function, every x has to have exactly one y. So every x has only one y. Or we also put it as it has to pass the vertical line test. So we're adding that is new is this one-to-one function. So it still has to be a function. Still every x has only one y value. So that mail still can't be ripped up and taken to two different mailboxes or mailman gets fired. It still has to pass the vertical line test, but to be one-to-one, it also has to pass the horizontal line test. So to be one-to-one function, it's going to have to pass the vertical and horizontal line test. So what I mean by this is that every x has only one y value, but every y has only one x. So kind of like how marriage should look. If we have something that is a function, so 1 can go to 11, and then 1 can't go to any other thing, but I can have another value that goes to 11, and that's not a big deal. So I could have 3 go to 17, and then 4 could go to 17 as well. That's kind of weird because I left out 13 and 19, but you get the picture. So this is a function, and it's still fine because I had those two pieces of mail that went to the same mailbox. In a one-to-one function, if 1 goes to 11, then nothing else can go to 11. So 1 still can't go to anything else because I can't rip up the mail, but I also can't have anything go to 11. So if 3 goes to 13, now nobody else can go to 13. 2 goes to 17. I'm just making this up, by the way, so don't read too much into where I pointed my arrows. But every x is linked with exactly one y and vice versa, so they can't have two arrows going to the same thing. So as far as looking at these functions, graphs on a graph, I'm looking to see if it passes that vertical line test to be a function, but then the same thing I'm looking for in a horizontal line test. So if there's any place where that horizontal line crosses two different y values, then it would not be, or x values, then it would not be a one-to-one function. So this is a function, and then it's also one-to-one, so this is a yes. So for our parabola, we know that it is a function, but it does not pass the horizontal line test, because it is going to cross twice. So that means that I had two x values that are going to the same y value. So I had something like this going on. And so if -3 goes to 3, I can't have anything else going to 3, just for example. So this is a no. And then don't forget, it does have to be a function. So still things like this, it doesn't pass that vertical line test. So don't be tricked by the ones that are not functions to begin with. So this would be a no as well, because it is not a function. It doesn't pass the vertical line test. So here's the big deal. If a function is one-to-one, then we know, and we're going to be talking about it a little more in a second, how to find it, but then we know that its inverse is a function, and that's important. So if a function is one-to-one, then its inverse is a function. So important stuff. If I'm going to be using a function and its inverse, it's important that I know that its inverse is a function. When I'm talking about an inverse, and this is something that you would have talked about in Algebra 2, The inverse of a function is literally changing the x's and the y's, or you could say the domain and range are swapped. There's a technical term for you. They're just swapped. So anything that was in the x values, now it's going to be a y. Anything that was a y is now an x. This is important to, This is important to come back to because we will have some challenging questions maybe with inverses, or maybe we forget how to find an inverse, but always going back to just the fact that our x's and y's are switched, that kind of helps us remember what we're supposed to do with it. So if we have a really simple example, and here's my f of x just saying what value goes to what y. By the way, this is our notation for the f inverse of x, or the f of x inverse. So this guy right here is the inverse of f of x when we have that little, kind of looks like it's to the -1 power, but it's our notation to say that we're talking about the inverse of f of x, or f inverse x is fine too. Since I'm switching my domain and my range, that means that now 5 is going to go to 1, we're going to have 10 go to 2, and 15 go to 3. So all of our y values became the x's became the y's. So you can see from this that we needed it to be 1-to-1, where every x had only one y and vice versa, so that when we switch it, it's still a function. If I try to flip these, then I'm going to end up having 11 be my x, going to 1 and 2 as y values, and that would not be a function. So that's why it's important for it to be 1-to-1. On a graph, same thing. I'm just switching the x's and the y's, but I just want you to see that if we find the inverse of, this is going to be our f of x, we can call it g of x, whatever you want. The inverse points, we're flipping that x and y, so we've got 0, -6, 4, 5, 6. We've got 6, -3. 6. That's -3. And then 9, 8. Right there. And then I'm just going to connect my segments from there. So not perfect, but you kind of get the gist. What I want you to see here is that our inverses are always symmetric about this line y equals x. So note that somewhere, that they're always symmetric. About that line y equals x. So it doesn't matter what functions we're dealing with, piecewise or otherwise. If we take the inverse of it, it is going to be symmetric, the original and the inverse. So this would be f inverse of x about that line y equals x. Okay, so what we're going to be dealing with more often is actually finding the inverses of a function algebraically. So again, I want to go back to just the very basics of inverses, the fact that my x's and my y's are switched. So in this case, I've got a function. What kind of function is it? What's it going to look like? I hope you said a line, because it is raised to the first power. Good job. So in order to find the inverse, and I always think it's important to some sort of note where you know that you're finding the inverse, because what we're about to do is not equivalent to this. It is something new. So to find the inverse, I'm still switching the x's and the y's just in my equation. So since this represents y, f of x, I'm going to swap it with my x. I'm just trading out my y for an x and my x for a y. So we need that notation somewhere in there, because this and this are not the same thing. Otherwise it looks like it's exactly the same thing. From here, we usually want to go ahead and resolve for y so that we can be looking at f inverse of x in that notation. So I'm just going to resolve for y, subtract my 3 over, and then dividing everything by 2. And it's usually a good idea at the end to go ahead and change back to the notation that I came from. So since it was f of x, I'm going to call this f inverse of x. Is this x minus 3 over 2. So that would be the inverse of this first one. Notice this, it's still a line, so that was a line, this is a line. If I graphed them both, because this has a slope of 2 and this has a slope of 1/2, they're just going to cross like this. Not perpendicular, but still reflecting over that y equals x. Okay. So our second one is going to be a little different because it is a different kind of function. What kind of function is that? Okay, I hope you said quadratic or parabola, or it's going to look like a U, or something like that. So we've got an upward facing parabola. How is it shifted? Okay, shifted up 16. It's fun to talk to myself here. So I'm finding the inverse. So my first step, again, going to swap out my x's for y's and my y's for x's. And then I'm resolving for my y value. Got x minus 16. And then to get y by itself, I'm taking the square root. And what do I have to remember when I take the square root of something? When I decide to take the square root of something, I've got to have that plus or minus. So I've got a plus or minus square root of x minus 16, and then changing back to my notation to say that this is f inverse. So this one, we knew that there would have to be something plus or minus in there because our original was parabolic. So we had this going, it was shifted up 16. I probably should have given myself more room for this, but shifted up 16. So let's just pretend that my vertex is up 16. There it is. I've got a small scale. But then we've got this plus or minus. So if I had forgotten that and I only had the plus, then I would only have this part where it's been shifted right 16, and then it's a radical function, so it's just going to be that top piece. So notice that I'm missing the bottom for it to be reflected about the x-axis, or sorry, about the line y equals x. Now sometimes they'll tell you x squared plus 16, and then they'll tell you the domain is x is greater than or equal to 0, and in that case we would only keep, because it was only talking about this piece, we would only keep the positive piece here as well. But if they don't give a restriction, then we want that whole thing so that it can be reflected about that line y equals x. All right. Our last thing that I'm going to look at is deciding if something is a one-to-one, or sorry, I read that too soon. Deciding if something is an inverse of another function. So if you're given two different functions, just trying to decide is f of x the inverse function of g of x and vice versa. So yes, you can start with this one and then find the inverse and see if it's g of x, but this is just kind of neat, and it does come into play a little bit, and also is a very easy way to check. You can kind of check in your head. But what should happen if they are inverses of each other is that when we take their composites, so when I find f of g of x, when I find g of f of x, I should get x both times. So let's start with f of g of x. And I'm rolling pretty fast through this to keep the video short, so if you need to pause it to write down the problem, do that. Don't let me leave you behind. You're on a video. So I'm plugging in everything that g of x has into the x and f of x. It might help to go ahead and write down f of x with a big old parenthesis there, to where I know my g of x is going in that spot. So I've got 3x plus 9. And then what should happen if they are inverses of each other is that you should have everything undo. It's like opposite operation city. So if I distribute my 1/3 to everything, I'll get an x, I'll get a positive 3, and then minus 3, which is just x. So you definitely need to show some work on this where you've set it up and then how you simplify, because there's really not a ton to show here because all those operations are going to undo each other. So that's what we wanted to happen. That's what tells us it is the inverse. We do have to check both though. It's very rare, but it could happen that one of them is x and the other one is not. And this is good practice for our composition of functions too. So in this case, I have my 3 times blah plus 9. I'm plugging in every part of f of x in for my x. So I've got a 1/3 x minus 3. And because these are both lines, it's going to work really similarly. When I distribute the 3 to everything, we'll get an x minus 9, then plus 9, which simplifies to x. So that just tells us it worked. Okay, last example that we're going to do together. So I do want you to go ahead and pause the video here and try this whole problem by yourself. You're first finding the inverse of the function, and then you're going to verify that it is the inverse by doing what we just did. So checking both composites and showing, yes, it is the inverse. And kind of similar to that last one because it is a line, but just checking to see that you can find the inverse, checking to see that it truly is. So go ahead and work it out. Pause it. If you haven't paused it, actually pause it. Did you pause it? Okay. I'm going to trust you. I'm going to work it out. So let's see our inverse here. Oh. I'll tell you what. The fact that I can't edit these is just real rough. Okay, so subtracting my 1, dividing by a -3. So I could make this look more like a line, so how we normally have -1/3 plus a positive third, but I'm going to leave it like that. We'll see what happens. If you went ahead and divided them both by a -3, that's fine, but you would have a -1/3 x plus 1/3. So make sure you divide it both by a -3. Okay, so here's our inverse. So first let's find, I didn't even use function notation here. That's okay. So first we're going to plug our answer into the original. It doesn't matter what order you did this in. So I can distribute here, but also I could just say that those cancel. Get an x minus 1 plus 1, which is just x. So the opposite is going to be plugging in this into my answer. So my -3x plus 1 minus 1 over a -3, where my 1's will subtract to be 0. I'm left with a -3x over -3, which is just x. Okay, so that's how we would check to make sure. You will have some in your homework where maybe you've got a radical and then you plug it in. This is just for example. Maybe you have something like this. So remember, you've got other opposite operations besides addition, subtraction, multiplication, division. If you plug it in and you have something like this, these do cancel each other out to end up with your x. So with these composition of functions, everything should just nicely undo each operation to end up with x, unless of course they're not inverse of each other, and then it will not work. Alright, so I can't edit this, so I can't blank out. What was I going to say at the end? I wasn't going to sing, that's for sure. That wasn't the plan. I don't know. Make sure you're following along with your Distance Friday sheet that was shared that has like the date on it, 9/11. That you're following along with each part of that so that you've graded yesterday's homework and asked any questions that you need to there, that you're following along with. Sometimes we'll have a Google Meet, sometimes I'll have a different way of you asking questions, but make sure that you're using this blocked off time to ask those questions and follow along with that sheet as best as possible. Let me know if you have questions, but we will always reconvene on Monday and kind of figure out some kinks, especially because this is the first one. So have a great weekend. You do have the homework that goes along with this, and I'll see you on Monday.